The morning of March 17th, 1943, broke humid and oppressive over the jungles of central Burma as Captain Hiroshi Tanaka knelt beside the captured American vehicle, his hands trembling not from the tropical heat, but from a realization that threatened to shatter everything he had believed about Japanese industrial prowess. The vehicle before him, a simple quarter-ton truck the Americans called a jeep, represented more than mere transportation. It represented a technological and industrial philosophy that made his nation's entire approach to manufacturing appear antiquated, almost medieval by comparison. Tanaka had graduated first in his class from the Tokyo Imperial University's School of Engineering in 1936, specializing in automotive design and manufacturing processes. He had spent 7 years at Kurogane Industries, helping develop Japan's Type 95 reconnaissance car, the nation's first mass-produced four-wheel drive vehicle. He had believed, with the fervent certainty of an engineer who understood specifications and capabilities, that Japanese automotive technology could compete with any nation on Earth. The Jeep, sitting before him, engine still warm from its capture just hours earlier, was about to prove him catastrophically wrong. The vehicle had been abandoned by retreating British forces near the village of Yanangyang as Japanese units advanced northward through Burma's central oil fields. Lieutenant Kenji Matsumoto, Tanaka's assistant and fellow graduate of Tokyo Imperial University, had supervised its recovery, carefully towing it, with a Type 95, back to their forward engineering depot for examination. The Americans had supplied thousands of these vehicles to British and Chinese forces through their Lend-Lease program, and Japanese intelligence desperately wanted to understand their capabilities. This was not the first American vehicle Tanaka had seen. There had been photographs in intelligence briefings, reports from other captured equipment, but this was the first time he would have the opportunity to conduct a thorough engineering analysis. Matsumoto approached with a leather satchel containing measuring instruments and notebooks, his uniform already dark with perspiration in the morning humidity. "Sir, the vehicle appears mechanically sound. The fuel tank was empty when we found it, suggesting deliberate abandonment rather than mechanical failure. The British left it by the roadside when they ran out of petrol during their withdrawal. I have prepared tools for complete disassembly and analysis." Tanaka nodded, but his attention remained fixed on the Jeep's overall design. Even before examining internal components, certain features struck him with unsettling implications. The vehicle's construction reflected manufacturing principles fundamentally different from Japanese approaches. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The chassis, formed from stamped steel channels rather than hand-fitted components, suggested mass production techniques on a scale Japan had never attempted. The body panels, simple flat or gently curved pieces, could be stamped by hydraulic presses in minutes rather than laboriously hand-formed over hours or days by skilled metalworkers. Everything about the design prioritized manufacturing speed and simplicity over traditional craftsmanship. The welds were clean and consistent, suggesting automated or semi-automated welding processes rather than individual craftsmen working with torch and filler rod. "We will begin with external examination and measurements," Tanaka instructed, pulling out his own notebook. "Document every dimension, every fastener type, every design choice. I want to understand not just what this vehicle can do, but how the Americans built it to be produced in quantity. That is the real intelligence value here." The two engineers spent the morning conducting a methodical survey that would eventually fill 43 pages of Tanaka's engineering notebook, supplemented by another 27 pages of detailed sketches and dimensional drawings by Lieutenant Matsumoto, who had some training as a technical draftsman before the war. The Jeep measured approximately 132 inches in length, 62 inches in width, and when equipped with its canvas top, stood roughly 70 inches tall. The wheelbase of exactly 80 inches provided exceptional stability on uneven terrain while keeping the turning radius surprisingly tight for a four-wheel drive vehicle. What immediately struck Tanaka was the vehicle's weight, or rather, its lack thereof. According to documents found in the Jeep's glove compartment, it weighed only 2,454 pounds empty, without crew or cargo. Japan's Type 95, designed for similar reconnaissance duties, weighed 2,420 pounds, but accommodated only 3 personnel, with far less cargo capacity and interior room. The Americans had achieved comparable weight, while providing significantly greater utility and functionality. The weight distribution revealed careful engineering thought. Tanaka noted that approximately 53% of the vehicle's mass rested on the front axle when unloaded, providing excellent traction for the powered front wheels when engaging four-wheel drive. The low center of gravity, combined with the wide 62-inch track and short 80-inch wheelbase, created a vehicle that would be nearly impossible to overturn under normal operating conditions. Lieutenant Matsumoto measured approach and departure angles with a surveyor's inclinometer borrowed from the engineering corps, finding them extraordinarily generous. 40 degrees front approach angle and 35 degrees rear departure angle, allowing the Jeep to navigate obstacles that would stop conventional vehicles dead in their tracks. "Sir, I have never seen such angles on a production vehicle," Matsumoto observed. "This suggests the Americans designed specifically for extreme off-road conditions, rather than compromising for on-road performance." Captain Tanaka turned his attention to the suspension system, and here his engineering assumptions began to systematically unravel. The Jeep utilized simple, semi-elliptical leaf springs, 7 leaves in front and 9 leaves in the rear, mounted directly to the axles with U-bolts and spring plates. Nothing sophisticated, nothing requiring advanced metallurgy or complex manufacturing processes, just basic leaf springs of the type that had been used on vehicles for decades. Yet the ride quality, even over Burma's primitive roads and jungle tracks, had reportedly been exceptional. According to interrogations of captured British personnel, the springs provided 9 inches of wheel travel, far exceeding the Type 95's capabilities of perhaps 5 or 6 inches. What troubled Tanaka deeply was not the engineering brilliance of the suspension design, because there was no particular brilliance involved, but its utter ordinariness. The Americans had achieved superior performance through nothing more than proper dimensioning, appropriate leaf thickness, and quality materials. The springs showed no signs of sagging or taking permanent set, despite obvious hard use in difficult terrain. The steel quality exceeded anything Japan's struggling metallurgical industry could consistently produce, especially now in 1943, with strategic materials becoming increasingly scarce. The axles presented another unsettling revelation that would haunt Tanaka's thoughts for days afterward. Both front and rear were live axles with open differentials, supplied by the Spicer Manufacturing Company, according to stampings on their housings. Tanaka knew Spicer as an American component supplier with decades of experience in drivetrain manufacturing, going back to the earliest days of automotive development. What shocked him profoundly was discovering these were not custom military components designed and built specifically for the Jeep, but rather commercial parts adapted from civilian vehicle production. The Americans had simply selected existing, proven designs from their vast civilian automotive industry and integrated them wholesale into military vehicles. The front axle even retained provisions for steering knuckles and kingpin assemblies that were clearly derived from civilian truck applications. Japan possessed no such industrial depth, no such reservoir of civilian automotive technology that could be simply requisitioned for military use. Every military vehicle component required custom design and manufacture by government arsenals or heavily supervised contractors. The Type 95's axles were unique to that vehicle, manufactured in small batches by a government-controlled supplier who made nothing else. The idea of simply requisitioning commercial parts and building military equipment around them was foreign to Japanese military procurement philosophy, which emphasized self-sufficiency and government control of military production. Yet, the Americans had done exactly that, and the result proved both superior in performance and vastly simpler to produce in quantity. It was a philosophical difference that spoke to fundamentally different approaches to industrial organization. "Sir, I have examined the wheels and tires in detail," Matsumoto reported, kneeling by the right front wheel. "The wheels are stamped steel, 16 inches in diameter, with 5 mounting bolts in a standardized pattern. The bolt circle appears to be 5.5 inches. The tires are commercial pattern, 6.00 by 16 inches, which is a standard civilian size. Both wheels and tires are entirely standardized and interchangeable. They show minimal wear despite obvious heavy use over rough terrain. The tread pattern is still clearly visible, with substantial depth remaining." Tanaka nodded, making detailed notes about this observation. Commercial tires on military vehicles represented yet another departure from Japanese practice that revealed America's industrial abundance. Japanese military vehicles used specialized tires, often manufactured in small batches by companies with limited rubber supplies and antiquated equipment. Each vehicle type required different tire specifications, creating logistics nightmares and supply bottlenecks. The Americans apparently had sufficient tire production capacity to equip military vehicles with commercial patterns, ensuring vast interchangeability and ease of replacement from civilian stockpiles if necessary. The transmission and transfer case examination began after a brief lunch of rice and dried fish, and here Tanaka encountered engineering that made him want to weep with professional frustration. The transmission was a simple 3-speed unit with a single reverse gear, manufactured by Warner Gear Company of Muncie, Indiana, according to casting marks on its housing. Nothing sophisticated, nothing requiring extraordinary precision or advanced materials. Yet the shifting action, even after obvious hard use in difficult conditions, remained smooth and positive. The synchronization between gears showed no signs of excessive wear or damage. The gear teeth, when Tanaka carefully examined them through the fill hole, appeared sharp and well-defined, without the rounding or pitting that typically developed in Japanese transmissions after extensive service. The transfer case, also supplied by Spicer Manufacturing, provided 2-speed operation in both 2-wheel and 4-wheel drive modes, giving the driver 4 distinct operational configurations. The design allowed the driver to select between high-range rear-wheel drive for normal road operation, high-range 4-wheel drive for moderate off-road conditions requiring extra traction, or low-range 4-wheel drive for extreme terrain and obstacle climbing. The shifting mechanism operated smoothly through a simple, floor-mounted lever that required no extraordinary effort to operate and featured positive detents that prevented accidental shifting between modes. "Lieutenant," Tanaka said quietly, his voice taking on a tone Matsumoto had never heard before, "examine the machining on these gears carefully. Note the surface finish, the precision of the tooth profiles, the quality of the case, hardening. This is production engineering of the highest order, yet these are mass-manufactured commercial components, not precision hand-fitted assemblies." Matsumoto studied the gears carefully through a magnifying glass, running his fingertips gently over the tooth surfaces. "Sir, these would be considered precision components in Japan, manufactured only in specialized shops under careful supervision by master craftsmen. The Americans appear to produce them on automated machinery with minimal hand finishing. The finish quality is uniform across all components, suggesting systematic process control rather than individual craftsmanship. Every gear tooth appears identical to its neighbors." That assessment contained the essence of what Tanaka was beginning to understand, a truth that grew more uncomfortable with each component he examined. Japanese manufacturing emphasized craftsmanship, the skill of individual workers producing components through careful, labor-intensive processes that required years of training and experience. American manufacturing emphasized systematic process control, machines producing components with such precision and consistency that they required minimal finishing and no individual fitting during assembly. The distinction represented not merely a difference in philosophical approach, but a fundamental gap in industrial capability that could not be bridged quickly or easily. The engine examination began in the late afternoon as the sun created dappled patterns through the jungle canopy overhead, insects buzzing in the humid air. Tanaka approached this portion of the analysis with both anticipation and dread, knowing that the engine would reveal the most profound differences between American and Japanese industrial philosophy. The Willys Go Devil engine, as the manufacturer somewhat whimsically called it, would tell him truths he was not sure he wanted to know. The engine displaced 134.2 cubic inches, equivalent to approximately 2.2 liters in the metric system Tanaka preferred for technical work. It was an L-head design, with the valves mounted in the engine block rather than the cylinder head, creating a simple, compact package with a low profile that contributed to the vehicle's excellent ground clearance. The configuration was not particularly sophisticated from an engineering standpoint, representing mature 1930s technology rather than cutting-edge design. Overhead valve engines offered better breathing and higher power output, but required more complex manufacturing. Yet, sophistication was not the point, Tanaka realized as he examined the engine more closely. The point was production, manufacturability, the ability to make thousands of these engines with consistent quality using semi-skilled labor. Tanaka carefully documented every aspect of the engine's manufacture, taking measurements and making sketches. The block was a single iron casting, with cylinders cast integrally rather than fitted as separate assemblies. The casting quality exceeded anything he had seen in Japanese manufacture, with uniform wall thickness throughout, clean internal passages without excessive coarse sand or casting flash, and minimal finishing required. The Americans had clearly mastered the art of precision casting on a mass production scale, controlling metal temperature, mold quality, and cooling rates to produce consistent results. The crankshaft, forged from high-quality steel and carefully balanced at the factory, ran in only 3 main bearings rather than the 5 or 7 typical of more sophisticated engines. The designers had accepted the higher bearing loads that came with wider bearing spacing in exchange for manufacturing simplicity and reduced parts count. The connecting rods were drop-forged steel, again of exceptional quality, with precision-machined bearing surfaces that showed minimal wear. Despite obvious hard use, the pistons were aluminum alloy, another indicator of American industrial capacity since Japan's aluminum production remained limited and closely controlled for aircraft manufacturing. Lieutenant Matsumoto carefully removed the cylinder head, exposing the combustion chambers for inspection. "Sir, the combustion chambers show typical carbon deposits consistent with extended operation, but no unusual wear patterns. The valves are seated properly with no signs of burning or distortion. The valve guides show acceptable clearances. This engine has clearly operated extensively under field conditions, but remains well within serviceable limits." "What is the stated service life expectation according to the technical manual?" Tanaka asked, knowing the answer would be revealing. Matsumoto consulted the vehicle's technical manual, which had been captured along with the Jeep. The manual indicates that major overhaul is not typically required before 60,000 miles of operation under normal conditions. Under severe military use, the interval is reduced to approximately 30,000 miles before major overhaul becomes necessary. 30,000 miles before major overhaul. Tanaka allowed that figure to settle in his mind, to sink in and reveal its full implications. Japanese military truck engines, maintained by skilled mechanics using carefully husbanded spare parts, typically required major intervention by 10,000 miles. If they were fortunate, many needed attention sooner. The Americans had designed and built an engine that lasted 3 times longer despite simpler construction and less sophisticated design. The explanation lay not in engineering brilliance, but in manufacturing quality and systematic process control. Every component, from pistons to bearings to gaskets, was manufactured to such exacting standards that proper assembly virtually guaranteed reliable operation. The Americans had made reliability a manufacturing objective rather than a maintenance achievement. They built quality into the components rather than trying to maintain it through careful service. The fuel system examination revealed another philosophical divergence that Tanaka found increasingly troubling. The Jeep used a simple mechanical fuel pump driven directly off the camshaft, feeding a single-barrel carburetor manufactured by Carter Carburetor Company. The entire fuel system could be removed and replaced by a moderately skilled mechanic in under an hour, perhaps 45 minutes, with practice. The fuel lines were steel tubing with simple compression fittings that required no special tools to service. The fuel filter was a replaceable cartridge type that simply unscrewed. Compare this to our Type 95 fuel system, Tanaka instructed Matsumoto. Note particularly the complexity of component replacement and the adjustment procedures required. Matsumoto nodded grimly, understanding the comparison his commander was drawing. "Sir, the Type 95 requires extensive disassembly to access the fuel pump, including removal of body panels and other components. The carburetor adjustment demands considerable skill and experience to achieve proper mixture across the operating range. We have lost vehicles to fuel system failures that would have been trivial to repair with this American design approach. A simple fuel pump failure that takes 10 minutes to repair on a Jeep might sideline a Type 95 for hours or even days. That was precisely the problem Tanaka was systematically documenting. Japanese vehicles incorporated sophisticated engineering, but poor design for manufacture and maintenance. American vehicles incorporated simple engineering, but excellent design for production and field repair. In sustained military operations, where maintenance facilities were limited and trained mechanics scarce, the latter approach proved vastly superior. A vehicle that was easy to repair would spend more time in service than a sophisticated vehicle that required specialized skills to maintain. The electrical system provided yet another revelation in the pattern Tanaka was discovering. The Jeep employed a 6-volt system, nothing sophisticated by contemporary standards, but executed with exceptional attention to manufacturability and reliability. The generator, voltage regulator, starter motor, and battery were all commercial components from established suppliers, likely pulled from the same parts bins used for civilian vehicle production. The wiring harness used color-coded insulation throughout and standardized connections, allowing rapid troubleshooting and repair even by personnel with limited electrical training. Each wire was clearly labeled at both ends. The routing was logical and protected from damage. Tanaka examined the lighting system with particular interest, knowing that vehicle lighting had been a persistent problem for Japanese military vehicles. The headlights, mounted under the hood, protected by the distinctive vertical slot grille, used sealed beam units where the entire assembly served as the bulb, lens, and reflector. When a headlight failed, the mechanic simply unplugged the unit and snapped in a replacement, a process taking perhaps 2 minutes. No adjustment was required, no alignment was necessary. The sealed beam design ensured consistent light output and made replacement trivial. Such sealed beam units would have been impossible to manufacture in Japan, Tanaka realized with growing frustration. The glass-forming techniques required to create the complex reflector surfaces, the precision optics needed for the lens, the vacuum sealing technology to prevent moisture intrusion, all exceeded Japanese industrial capabilities. The Americans had designed lighting systems assuming access to advanced manufacturing capacity that Japan simply lacked and could not quickly develop. As evening approached and the jungle sounds grew louder with the coming night, Captain Tanaka sat on an ammunition crate and began drafting his preliminary assessment, watching the sun filter through the trees. The vehicle before him represented more than superior engineering or clever design. It represented an industrial system so far beyond Japanese capabilities that meaningful comparison seemed almost pointless. The Jeep's entire design philosophy emphasized manufacturing efficiency at every single level, from the largest structural components down to the smallest fasteners. Components were designed for production on automated machinery rather than by skilled craftsmen working with hand tools. Tolerances were specified to ensure interchangeability rather than requiring individual fitting and adjustment during assembly. Assembly procedures assumed semi-skilled workers following systematic, documented processes rather than experienced mechanics applying judgment and expertise developed over years of training. Every design choice, without exception, prioritized quantity production over manufacturing sophistication. And yet, the result was not crude or unreliable or shoddily built. The result was a vehicle that outperformed Japanese equivalents in virtually every measurable parameter, while being vastly easier to build, maintain, and repair in field conditions. The genius of American automotive engineering, Tanaka was beginning to understand, lay not in technical sophistication, but in systematic simplification. Tanaka thought about the numbers that intelligence reports had provided, numbers that now carried new meaning after his examination. According to the best available intelligence, the Americans had manufactured approximately 640,000 Jeeps between 1941 and the present date. In March 1943, 640,000 identical vehicles, each built to specifications so precise that components from vehicles manufactured in different factories by different contractors could be freely interchanged without fitting or adjustment. That level of standardization represented industrial capability that Japan had never achieved. Japan had manufactured approximately 4,800 Type 95 reconnaissance vehicles over 7 years of production from 1936 to 1943. Doing the mathematics in his head, Tanaka calculated that the Americans built more Jeeps in a single month, approximately 32,000 vehicles, than Japan had built reconnaissance vehicles in its entire history. The disparity was so large, it seemed almost meaningless, like comparing different orders of magnitude rather than different quantities. The mathematical implications were staggering and deeply troubling. In the time required for Japanese industry to produce one reconnaissance vehicle with all its hand-fitted components and careful assembly, American industry produced approximately 133 Jeeps using automated machinery and systematic processes. The disparity could not be explained by superior American design or engineering genius. Japanese engineers were just as capable, just as well-trained, just as intelligent as their American counterparts. Tanaka knew this absolutely from his own education and experience. The disparity existed because America possessed an industrial system that had spent decades, since the late 1800s, developing mass production techniques, machine tools, process controls, quality systems, and manufacturing infrastructure that Japan had barely begun to create. Henry Ford's moving assembly line dated to 1913, 30 years of accumulated experience in volume production. Japan's automotive industry barely existed before the 1930s, perhaps 15 years of serious development at most. That 30-year gap in industrial development could not be closed quickly or easily, certainly not during a war when resources were limited and priorities constantly shifting. Lieutenant Matsumoto returned from arranging their quarters for the night, carrying a pot of tea prepared by their camp kitchen staff. "Sir, I have arranged for the vehicle to be placed under armed guard overnight. Tomorrow we can begin detailed disassembly of the drivetrain components, as you planned." Tanaka accepted the tea gratefully, but found himself without appetite, despite not having eaten properly since morning. "Matsumoto, I need you to understand something that my preliminary examination has revealed. This vehicle is not simply well-engineered in the conventional sense. It is designed specifically for mass production by a nation with industrial capabilities we cannot match, not now and perhaps not for decades. Every component, every design choice reflects assumptions about manufacturing capacity that do not apply to Japan." That statement hung in the humid evening air, heavy with implications that both men understood but were reluctant to voice explicitly. Matsumoto set down his own teacup, giving Tanaka his full attention with the respect due a superior officer, but also the concern of a fellow engineer who sensed where this analysis was leading. "Sir, I have observed many of the same features you documented today. That's the standardization, the precision machining, the quality of materials, the systematic approach to design for manufacture. But surely we can learn from this design and improve our own vehicles based on these lessons. Surely this intelligence has value for our development programs. We can learn, yes, Tanaka replied carefully, aware that his next words might be construed as defeatist if reported to the wrong ears. But implementing what we learn requires industrial infrastructure we do not possess and cannot quickly create. The Americans built this vehicle assuming they have automated stamping presses, precision casting facilities, systematic quality control systems, and extensive networks of component suppliers that Japan lacks. We cannot simply copy the Jeep's design because we cannot manufacture the components from which it is built. Our machine tools lack the necessary precision. Our metallurgy cannot consistently produce the required material quality. Our supplier base does not exist. These are not problems that can be solved through engineering effort alone. They require capital investment, workforce training, and time measured in years or decades, not months. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Matsumoto absorbed this sobering assessment, the implications settling over him like the evening darkness gathering in the jungle around their camp. Then what do we recommend, sir? What purpose does this analysis serve if we cannot apply its lessons to improve our own capabilities? What do we tell headquarters when they ask for recommendations? Tanaka opened his notebook and began writing by the light of a kerosene lantern that attracted swarms of insects. We document everything with complete honesty because someone, somewhere in Japan's industrial hierarchy, must understand the true scale of the challenge we face. This Jeep reveals that America fights with an industrial system specifically designed and optimized for mass production of complex mechanical devices. We fight with an industrial system that is still transitioning from craft production methods to modern manufacturing. That gap cannot be closed during the course of this current war. Perhaps it cannot be closed in a generation. But it must be acknowledged and understood if Japan is to have any hope of industrial development in the future. The words felt dangerous to write, verging on treasonous in their implications, but Tanaka's engineering training demanded absolute honesty about technical realities. His obligation as an officer was to provide accurate intelligence and assessment, not comfortable reassurances. The Jeep sitting before him in the gathering darkness was not a miracle of American innovation or a product of superior American engineering genius. It was the logical, inevitable product of an industrial economy that had spent half a century systematically developing manufacturing capabilities, building layer upon layer of industrial infrastructure, training generation after generation of skilled workers, accumulating knowledge and experience in volume production. Japan had begun that same journey decades later and remained far behind, struggling to catch up while simultaneously fighting a war that consumed resources and diverted attention from industrial development. The night sounds of the Burma jungle provided an ominous backdrop to Tanaka's writing as he worked by lamplight, documenting his observations and preliminary conclusions. Somewhere in the darkness, beyond their camp perimeter, the war continued its relentless progression. Japanese forces advanced through Burma, capturing territory and driving British and Chinese forces before them in tactical victories that demonstrated Japanese military skill and determination. These tactical successes created and sustained the illusion of Japanese military superiority, reinforcing the comforting belief that warrior spirit and tactical excellence could overcome material disadvantages. Senior officers spoke confidently of ultimate victory through superior morale and fighting spirit. Captain Tanaka, sitting in a tent that barely kept out the jungle humidity, examining an abandoned Jeep by lamplight, understood a profoundly different truth that would haunt him for the rest of his life. Modern warfare in the 20th century was decided not on battlefields where courage and tactics mattered, but in factories where production capacity and industrial efficiency determined outcomes with mathematical certainty. Japan might win individual battles through courage, tactical skill, and tactical excellence. Japanese soldiers were among the finest fighters in the world, motivated by deep cultural values and willing to sacrifice everything for their emperor and nation. But Japan would ultimately lose the war through industrial inadequacy, through the simple mathematical reality that it could not replace losses as fast as the enemy could inflict them, could not produce equipment in the quantities modern warfare demanded, could not sustain the logistics necessary to support far-flung military operations. The Jeep was merely one piece of evidence among many, but it was concrete proof that could not be dismissed or explained away. It was a physical object he could measure and document, providing irrefutable data about American industrial capabilities. An ordinary vehicle, nothing particularly sophisticated or representing breakthrough technology, just a simple truck, designed and manufactured by a nation that had mastered the industrial arts to a degree Japan had not yet achieved, and perhaps might never achieve. The implications extended far beyond reconnaissance vehicles or even military equipment generally. If Americans could produce Jeeps with such remarkable efficiency, achieving this level of standardization and manufacturing quality, then they could produce tanks, aircraft, ships, weapons, ammunition, and all the other material of war with similar systematic efficiency. They could replace losses faster than Japan could inflict them. No matter how successfully Japanese forces fought individual battles, they could equip their forces with such abundance that Japanese scarcity would become an insurmountable handicap, a gap that courage alone could not bridge. Tanaka thought about his father, who had fought in the Russo-Japanese War of 1905 when Japan's surprise naval victory over Imperial Russia at the Battle of Tsushima Strait had announced the empire's arrival as a modern military power capable of defeating European nations. That stunning victory had fed decades of confidence in Japanese martial superiority, creating the deeply held belief that Japanese forces could overcome any opponent through discipline, tactical skill, and fighting spirit. The victory had been real and significant, but it had also created dangerous overconfidence. But 1905. Japan had fought Russia, certainly an industrial power, but one hampered by primitive logistics, internal political weakness, and the need to supply forces across thousands of miles of single-track railroad. 1943. Japan was fighting America, an industrial superpower with logistical capabilities that made distance nearly irrelevant and manufacturing capacity that made losses easily replaceable. The strategic situation could hardly be more different, yet Japanese military planning seemed to assume the same factors that led to victory in 1905 would produce victory now. It was a fundamental misunderstanding of how warfare had changed in the industrial age. March 18th, 1943, dawned with the same oppressive humidity as the previous day, moisture hanging in the air and condensing on every metal surface. Captain Tanaka woke early after a restless night, troubled by dreams of endless assembly lines, producing vehicles faster than he could count. He began the detailed disassembly he had planned, methodically removing components one at a time and documenting their construction methods with photographs, sketches, and detailed notes. Each piece he examined, reinforced and expanded his initial assessment, adding more layers of evidence to conclusions he increasingly wished were wrong. The brake system employed hydraulic actuation with fluid pressure from a master cylinder mounted on the firewall, transmitting force through steel lines to wheel cylinders at each wheel. Hydraulic brakes offered dramatically superior stopping power compared to mechanical systems, required less physical effort from the driver, and provided more consistent, reliable performance. The hydraulic lines were formed steel tubing with threaded fittings and flexible hoses at the wheels to accommodate suspension movement, easily replaced in field conditions with basic tools. The wheel cylinders were simple two-piston designs that could be rebuilt with minimal expertise using standard rebuild kits. Japan had begun adopting hydraulic brakes on some military vehicles, recognizing their advantages. But the manufacturing infrastructure to produce reliable hydraulic components at scale barely existed in Japanese industry. Brake fluid leaks plagued Japanese vehicle operations because the quality control and precision machining required to ensure leak-free hydraulic systems exceeded the capabilities of many component suppliers working with worn machine tools and insufficient quality inspection. Seals degraded quickly, cylinders scored easily, fluid contamination caused failures. The Americans had evidently solved all these manufacturing challenges years earlier, probably in the 1920s or early 30s, when hydraulic brakes first appeared on civilian vehicles, accumulating decades of experience in producing reliable hydraulic components. The steering system employed a Ross steering gear, a recirculating ball design that provided precise control with minimal play and required less effort than simpler worm and sector designs. The steering geometry had been very carefully calculated to provide natural centering and minimal kickback over rough terrain, making the vehicle easier to control and reducing driver fatigue during long-distance operation. The tie rods and drag link used tapered roller bearings in the steering knuckles, providing both exceptional strength and easy serviceability. The front wheels could be aligned using simple measurements and basic hand tools, no sophisticated equipment required. Lieutenant Matsumoto examined the front suspension attachment points with an engineer's attention to detail. "Sir, the frame is designed with specific, precisely located mounting points for all suspension and steering components. Everything attaches with standardized bolts in accurately positioned holes, and there is no provision for adjustment or hand-fitting during assembly. This means the components themselves must be manufactured to such tight tolerances that they simply bolt together in correct alignment. There is no room for error, no opportunity for a skilled assembler to compensate for imprecise manufacturing. Every component must be right the first time, every time." That observation captured yet another fundamental difference between Japanese and American approaches to manufacturing. Japanese vehicle assembly required skilled workers making continuous adjustments, adding shims where necessary, filing or grinding components to achieve proper fit, making hundreds of small decisions during the assembly process. American vehicle assembly assumed components manufactured to such precision that no individual attention was required or even possible. The first approach demanded craftsmanship and judgment. The second approach demanded industrial capability and systematic process control. It was the difference between making things by hand and making things by machine, between craft production and mass production, between the 19th century and the 20th. Tanaka spent most of the afternoon examining the transfer case in exhaustive detail, documenting its elegant simplicity with photographs and dimensional drawings. The unit allowed power flow in 4 different modes: two-wheel drive, high range, for normal road travel; four-wheel drive, high range, for improved traction in moderate conditions; four-wheel drive, low range, for extreme off-road operation and obstacle climbing; and even provision for power takeoff to operate auxiliary equipment, like winches or generators. The shifting mechanism between these modes was completely foolproof, physically preventing impossible gear selections that might damage components. A driver could shift confidently without detailed technical knowledge. The gearing was robust enough for the anticipated loads with safety factors that suggested the designers had prioritized reliability and durability over achieving minimum weight or size. Every aspect of the transfer case reflected mature engineering informed by years of experience with four-wheel drive vehicles in civilian and commercial applications. The Americans had not invented these concepts specifically for the Jeep, had not started from scratch with military requirements. They had simply applied proven designs from decades of civilian and commercial vehicle production, selecting components and configurations that balanced performance, manufacturability, durability, and cost. They stood on the shoulders of industrial giants, benefiting from accumulated knowledge and experience that Japan's younger automotive industry had not yet developed. The body construction revealed perhaps the most striking divergence from Japanese automotive philosophy. the clearest evidence of how completely American design prioritized manufacturing efficiency. The Jeep's body consisted entirely of flat panels or panels with only gentle, simple curves that could be stamped from sheet steel on hydraulic presses in single operations. And there were absolutely no compound curves, no sections that curved in two directions simultaneously, no components requiring skilled metal workers with hammers and English wheels to form complex shapes by hand. Even the relatively curved fenders were actually simple, rectangular sections with minimal flare, easily formed with basic dies. The hood consisted of three essentially flat panels joined at shallow angles. The cowl and firewall were formed from gently curved sheets that required no specialized forming. Even the seats were nothing but simple frames with canvas covering stretched over them. The entire design reflected the fundamental assumption that vehicles would be manufactured in quantities so astronomically large that even trivial savings in component production time would multiply into significant overall efficiency gains when spread across hundreds of thousands of units. If stamping each body panel took 30 seconds instead of 35 seconds, a mere 5-second savings, that difference, multiplied by 640,000 vehicles, yielded savings of nearly 900,000 seconds, or approximately 250 hours of press time saved, across all the vehicle's components. Such incremental savings accumulated into dramatic differences in total manufacturing time and labor requirements. Japan's Type 95, by contrast, featured body components that required substantial hand finishing by skilled metalworkers. Compound curves needed to be formed carefully by workers with years of training, checking progress frequently and making continuous adjustments. Panels required individual fitting during assembly because small variations in hand-formed components meant nothing was quite identical. The design assumed and required that vehicles would be produced in small batches by skilled craftsmen who took pride in their work and possessed the expertise to create complex shapes from flat-sheet metal. That assumption made perfect sense for a nation with limited industrial capacity but substantial reserves of skilled manual labor. But it also meant Japanese vehicle production could never hope to scale to the volumes modern industrialized warfare demanded. You simply could not train metal workers fast enough, could not find enough skilled craftsmen to produce vehicles in the hundreds of thousands. Captain Tanaka photographed the Jeep extensively using a captured American camera loaded with film requisitioned from enemy supplies, carefully documenting design features that words struggled to adequately convey. The photographs would accompany his written report, providing visual evidence of American manufacturing philosophy for engineers and officials who had never seen these vehicles firsthand and might not fully grasp the implications from text descriptions alone. As the sun began its descent on March 18th, casting long shadows through the jungle, Lieutenant Matsumoto approached with unexpected and somewhat unwelcome news, his expression suggesting the message was not entirely welcome. "Sir, Headquarters has radioed specific instructions regarding our analysis. We are to prepare a comprehensive written report on this vehicle within 48 hours. The report will be forwarded to Tokyo for detailed evaluation by the Army Technical Bureau and senior planning staff. They specifically request assessment of whether Japanese industry can manufacture a similar vehicle using our current capabilities, and if not, what would be required to develop such capability. They want to know if we can copy American designs." Tanaka felt a cold weight settle in his stomach, understanding immediately the difficult position in which headquarters had placed him by requesting an honest assessment of a question with no good answer. They want to know if we can copy the Jeep, build our own version based on this design. "Precisely, sir." They reference recent captures of American tanks and aircraft, stating that understanding enemy equipment capabilities is essential for planning both countermeasures and potentially developing equivalent Japanese designs if feasible. They want honest technical evaluation from engineering specialists in the field. Tanaka nodded slowly, understanding both the importance of the request and the impossible position it created for him personally. They wanted technical assessment, free from defeatism or unwarranted pessimism. Yet, intellectually honest technical assessment would inevitably reveal profoundly uncomfortable truths about Japanese industrial limitations that some officers would prefer not to acknowledge or confront. Speaking such truths could be career-ending, or worse, in a military culture that increasingly valued optimism and fighting spirit over uncomfortable realities. I will draft the comprehensive report tonight and tomorrow as ordered, Tanaka said with resignation. You will assist with compiling technical specifications and measurements from your notes. We will be completely honest about what we have observed and documented, even if that honesty proves unwelcome to some recipients. Matsumoto hesitated visibly, then spoke carefully with obvious concern. Sir, permission to speak freely about a sensitive matter? Always granted between us, Lieutenant. You know that. Some officers in other units have been relieved of command or face serious consequences for submitting what headquarters termed pessimistic or defeatist reports about enemy capabilities or unfavorable assessments of strategic situations. The High Command increasingly prefers to emphasize Japanese advantages and favorable factors rather than acknowledge uncomfortable enemy strengths or difficult realities. Your report, if it honestly addresses manufacturing capabilities, may be poorly received by some officials. Tanaka understood the warning and genuinely appreciated Matsumoto's concern for his welfare, but he firmly rejected the implication that he should shade his analysis to make it more palatable. I am an engineer first, Lieutenant, not a propaganda officer or political operative. If the Army Technical Bureau wants honest technical assessment, they will receive exactly that from me. If they prefer comfortable lies or reassuring fiction, they should assign this analysis to someone more willing to compromise technical integrity for political considerations. My duty is to report truth as I understand it through systematic engineering analysis, not to tell senior officers what they want to hear. That evening, working by the uncertain light of a kerosene lamp that attracted swarms of insects, Captain Tanaka began drafting what would prove to be the most important, most controversial, and potentially most career-ending document he would write during his entire military service in the war. He chose his words with great care, knowing that every sentence would be scrutinized by officials looking either for useful intelligence or for evidence of defeatist thinking, depending on their own preconceptions and attitudes. Subject: technical analysis of captured American quarter-ton truck, four-wheel drive, Model MB, commonly designated Jeep. Summary: the captured vehicle represents a sophisticated and mature example of mass production engineering designed specifically and explicitly for maximum manufacturing efficiency rather than technical sophistication. The design consistently prioritizes standardization, interchangeability, ease of assembly, and field maintainability across all systems and components, while individual components are not technologically advanced or representing breakthrough innovations. The overall integration, systematic design approach, and implicit manufacturing assumptions represent industrial capabilities significantly exceeding those currently available in Japan. Tanaka paused, reading what he had written with a critical eye. Already, the implications were clear and uncomfortable, even in a brief summary. He continued, knowing that each additional sentence would likely cause increasing discomfort among officers who believed Japanese spirit could overcome material disadvantages. Detailed observations. The vehicle employs approximately 2,000 individual components, of which approximately 95% are standardized parts manufactured to precision tolerances specifically intended to allow complete interchangeability between vehicles without individual fitting or adjustment. Components are systematically designed for production on automated or semi-automated machinery, with minimal hand finishing required after machining or forming operations. Assembly procedures clearly assume semi-skilled workers following documented systematic processes and standard work instructions, rather than experienced craftsmen applying individual judgment and expertise developed over years of training and apprenticeship. Tanaka continued writing through the night as insects buzzed around his lamp and the jungle sounds of nocturnal animals echoed in the darkness beyond the camp perimeter. He documented the engine's manufacturing quality, noting casting precision and material consistency. He described the transmission and transfer case, emphasizing their origins as commercial components adapted for military use. He detailed the body construction, explaining how every panel had been designed specifically for rapid stamping operations. Each technical observation reinforced his central conclusion that the Jeep represented not engineering brilliance, but systematic industrial capability. In the most difficult section, the one he had been mentally drafting and redrafting in his mind, addressed the question headquarters had specifically posed: whether Japan could manufacture a similar vehicle using current capabilities. Tanaka chose his words with extreme care, knowing this section would draw the most scrutiny and potentially the harshest criticism. Manufacturing feasibility assessment. Japan cannot manufacture a vehicle equivalent to the American Jeep within any timeline relevant to current military operations. This conclusion derives not from fundamental technological limitations or theoretical impossibility, but from practical industrial capacity constraints that cannot be adequately addressed through engineering effort alone, regardless of resources committed. The specific insurmountable obstacles are as follows. First, component manufacturing precision. American Jeeps employ components manufactured to tolerances that Japanese suppliers cannot consistently achieve with existing machinery and current quality control processes. The precision required is not extraordinary by American standards, but exceeds the practical capabilities of much of Japanese industry, using worn or outdated machine tools with insufficient process controls. Establishing equivalent precision would require wholesale modernization of machine tool infrastructure across numerous suppliers, a process requiring years of time and substantial capital investment that is not available during wartime. Second, materials quality and availability. The Jeep design assumes ready access to high-quality steel, aluminum alloys, rubber, and other materials in quantities that Japan cannot currently supply on a sustained basis. Even if manufacturing precision could somehow be achieved through extraordinary effort, chronic material shortages and quality inconsistencies would prevent sustained production at necessary volumes. Japan's steel production, while substantial, cannot match American output in either quantity or consistent quality, particularly for specialty alloys requiring precise metallurgical control. Third, supplier network depth and industrial ecosystem. American Jeep production relies on extensive networks of specialized component suppliers providing standardized parts, Spicer for axles and transfer cases, Warner gear for transmissions, Carter for carburetors, and numerous others. Each supplier brings decades of experience and established production capabilities. Japan lacks any equivalent supplier infrastructure, requiring military arsenals to manufacture most components in-house, which severely limits production capacity and prevents the division of labor that enables American production volumes. Creating such a supplier network would require years of industrial development that cannot be compressed into shorter timeframes, regardless of urgency. Fourth, industrial knowledge and accumulated experience. American automotive engineers and production personnel benefit from approximately 40 years of mass production experience dating to Henry Ford's moving assembly line. Japanese automotive industry has perhaps 15 years of serious development. This experience gap cannot be closed quickly because it represents accumulated practical knowledge that must be learned through actual production experience, not simply copied from technical documents. The sun was rising on March 19th as Captain Tanaka set down his pen, having written through the entire night without rest, his hand cramped from hours of careful calligraphy. But the report was essentially complete, except for recommendations. Lieutenant Matsumoto entered the tent carrying tea and rice, his face showing concern at seeing his commander still working. "Sir, You have been writing all night without sleep. You should rest before completing the report and reviewing it. Your health matters. I am nearly finished, Lieutenant. Only the recommendations section remains, and then a final review of the entire document. Matsumoto set down the food and glanced at the report with permission from Tanaka's gesture. Sir, I read the summary and feasibility assessment paragraphs. Your assessment is quite direct and specific, pulling no punches. Possibly too direct for comfortable reception by some recipients. Tanaka picked up his pen again, accepting the tea, but leaving the food untouched. But technically accurate, yes? Have I misstated any facts or drawn conclusions not supported by our systematic examination? No, sir. The assessment is entirely accurate based on what we documented. That is precisely what concerns me about potential reactions. The recommendation section. When Tanaka finally wrote it, after drinking the tea and eating a few bites of rice, attempted to balance technical honesty with constructive forward-looking suggestions that might make the report's overall pessimistic conclusions slightly more palatable to officials seeking actionable recommendations rather than merely honest but discouraging assessments. Recommendations. Japan should not attempt to directly copy the American Jeep design in any comprehensive way, as this would require industrial capabilities that do not currently exist and cannot be quickly developed even with unlimited resources and absolute priority. Such an attempt would consume scarce engineering talent and limited manufacturing capacity in pursuit of an unachievable objective, producing frustration without meaningful results. Instead, Japanese vehicle development efforts should focus on designs that realistically accommodate existing manufacturing capabilities while incorporating specific lessons learned from American production philosophy where practically applicable given current constraints. Specifically, future Japanese vehicle designs should emphasize standardization of components to the maximum extent practical given current manufacturing precision limitations, simplification of body construction to reduce hand-forming requirements where possible without compromising functional requirements, conscious design for maintainability, ensuring that field repairs can be accomplished with basic tools and minimal specialized knowledge, realistic production targeting based on actual rather than theoretical manufacturing capacity, avoiding commitments that cannot be fulfilled. Additionally, long-term industrial development planning must prioritize the following critical investments for Japan's industrial future. Machine tool modernization programs to improve component manufacturing precision across the industrial base. Metallurgical process improvements to ensure consistent material quality for critical components. Development of specialized supplier networks capable of providing standardized components to multiple vehicle manufacturers. Comprehensive training programs to develop workforce skills in modern manufacturing techniques and quality control methods. These improvements cannot realistically be accomplished during the current conflict, but represent essential investments for Japan's industrial future and economic competitiveness, regardless of immediate military outcomes. That final sentence represented Tanaka's most dangerous assertion, the most potentially treasonous implication in the entire report, the subtle suggestion that Japan should plan for industrial development regardless of whether the war resulted in victory or defeat. Such thinking could easily be construed as defeatist, as acknowledging possibilities other than ultimate triumph. But Tanaka believed absolutely that technical honesty demanded including it. Japan would need modern industrial capabilities in any future scenario, and pretending otherwise served no useful purpose. Lieutenant Matsumoto read the completed report with great care over the next hour, checking technical specifications against his own notes and evaluating the logic of Tanaka's arguments. Sir, this is thorough, technically rigorous, and brutally honest about uncomfortable realities. It is also likely to cause you significant personal and professional difficulty with senior officers who prefer more optimistic assessments that emphasize potential solutions rather than acknowledging fundamental limitations. Then I will have performed my duty as an engineer and as an officer, Tanaka replied firmly, even if it cost me my career, or worse, Technical reality does not change to accommodate optimistic preferences or wishful thinking. The Jeep possesses the capabilities we documented, whether we acknowledge them or not. American industrial capacity exists at the levels we described, whether we admit it publicly or not. Denying uncomfortable truths does not make them less true. It merely ensures we make decisions based on fiction rather than reality. Tanaka sealed the report in an envelope marked for immediate courier delivery to Tokyo via the fastest available route, understanding that he was committing his professional fate and possibly more to the honest conclusions he had documented. The report, all 27 pages of careful technical analysis supplemented by 43 pages of dimensional drawings and detailed specifications, was dispatched on the afternoon of March 19th aboard a courier aircraft flying from Burma to Rangoon, from where it would be forwarded through military channels to Tokyo and the Army Technical Bureau. Captain Hiroshi Tanaka returned to his routine engineering duties afterward, supervising the maintenance of Japanese vehicles in his engineering battalion and conducting minor field repairs on equipment that increasingly suffered from the same fundamental manufacturing inadequacies he had documented in his Jeep analysis. 3 weeks passed without any acknowledgement of his report from headquarters, without any indication that it had even been received. Tanaka assumed it had been filed away in some dusty archive, perhaps unread, possibly read and quietly dismissed as pessimistic defeatism unworthy of official response. Then, on April 11th, 1943, unexpected orders arrived by courier, transferring Captain Tanaka to Tokyo for immediate consultation with the Army Technical Bureau regarding captured enemy equipment analysis and assessment methodologies. The orders came without explanation, without indication whether he was being recalled for commendation or court-martial. He had 48 hours to arrange transfer of his duties and report to headquarters in Tokyo. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.